Black holes don't just bend time, they make it slow down, without even physically touching it. This might sound counterintuitive, but it's a proven reality. On Earth, we've already conducted experiments to show that this phenomenon can truly occur. You might have heard about the atomic clock height experiment. In this experiment, scientists placed one atomic clock at ground level and another a few centimeters higher on a shelf. The result was fascinating. The clock on the shelf ticked faster than the one on the ground. The simple change in height caused time to be out of sync. It's not magic, it's a rule of physics at play. In the energy filament theory, we can explain this phenomenon in a straightforward way. The greater the tension, the slower the rhythm of the particles. The lesser the tension, the faster the rhythm of the particles. Atomic clocks measure time by the vibration rhythms of particles. On Earth, the tension is higher at ground level, causing particles to vibrate more slowly, which means time runs slightly slower. On the shelf, where the tension is weaker, particles vibrate faster, and as a result, time runs slightly faster. Even a small change in height, just a few centimeters, can lead to a noticeable effect on time. Now, imagine taking this concept and applying it to the extreme tension near a black hole. The Earth's tension is like gently pressing on a rubber membrane, but near a black hole, the tension is much more intense, like squeezing a bubble membrane to the brink of bursting. According to the energy filament theory, this is the most extreme tension field in the universe. When an electron gets close to the outer critical boundary of a black hole, its internal vibration rhythm gets stretched out. Just like when you stretch a spring, it takes longer for it to vibrate. As a result, the particle's rhythm slows down. And because time is directly tied to these vibrations, time itself slows down. From an outside observer's point of view, it seems like everything near the black hole moves incredibly slowly, almost as if someone had pressed the slow motion button on time, reducing its speed to 1/4 of its usual pace. In the energy filament theory, we don't invoke mysterious or unexplained time distortions. Instead, there is a simple, fundamental rule: time equals the rhythm of the particles. When tension stretches the rhythm, time stretches as well. This explains why, near a black hole, time appears to almost freeze. The tension there is so extreme that the particles' rhythms are stretched to their limits. And naturally, time slows down in this environment, dragged into an abyss. To truly understand why time slows down in such situations, we need to revisit the fundamentals of the theory, starting with the electron's rhythm and the way tension affects it. Time, in essence, is not an independent coordinate in space, but a phenomenon that depends on the rhythm of the particles. The tension in the field controls the pace at which time flows. In our next episode, we'll explore why black holes can influence the structure of entire galaxies. Tap follow, share it on New Physics, Clear Universe.